people in Europe.
Okay, all right.
It looks like there's a group missing.
Yeah. Like, I don't think Kara.
So we're a little bit behind, but we can just try to have it most people. So welcome to the afternoon session on, well, mostly larger scales, but also the same. So first up we have Rob.
Can you hear me? Yeah. Okay. So, hi, I'm Robin Tress. I'm a PhD student in Heidelberg, working in a group of Ralf Klessen. And I'm happy today to talk a little bit about our work of the Central Molecular Zone. So, I just come from an unconference session about extreme star formation. And in our Milky Way, the Central Molecular Zone is exactly that, a region of extreme star formation in the very center of our Milky Way. And as the name suggests, it's an accumulation of molecular gas in the few hundred parsecs in the center of our Milky Way. But to understand how actually we end up with this accumulation of molecular gas in the center, we have to look at the broader picture of our galaxy. And we noticed that actually our galaxy is barred, so it has a bar. And with this talk, I would like to convince you that the motions, the behavior of the gas in the presence of a bar are extremely important in shaping the central molecular zone. And it is therefore extremely important to consider the whole region if we want to understand the very center. To understand how the bar influences the evolution and the motions of the gas, we first consider closed ballistic orbits, and we can see that there are basically two families of orbits. Outside we have X1 orbits, which are elongated in the direction of the bar, and in the inside we have so-called X2 orbits, which are orbits elongated in the other direction, perpendicular to the bar. The gas behaves in a similar manner. So outside we have these X1 orbits. The gas flows in these closed X1 orbits. And in the very center we have basically a disk of X2 orbits. The major and fundamental difference between ballistic closed orbits and the gas is in this intermediate region where the orbits are self-intersecting, and the gas therefore forms strong shocks which connect the tip of the bar to the central X2 disk. And in our Milky Way, the central molecular zone is associated to one of this X2 disk. Here are a few pretty pictures where you can clearly see the features that I just described of externally face-on galaxies. For our own Milky Way, we have the problem that we actually are inside the disk and we don't have a face-on view of our own Milky Way. So we deal with these latitude line-of-sight velocities plots. And we have to use the information that are stored in these plots, and with the help of models, we try to understand what the 3D, what the face-on view of the Milky Way would look like. So here I show in black and white the CO emission and a much higher density tracer in the yellow, which is ammonia. So from these kind of observations, it becomes evident that the emission is actually asymmetric, and the major part of the emission comes from positive longitudes. And this was clear since a long time, so already in 1988 this was pointed out. But since now there's no good way to actually give an explanation to that. So in our model to actually consider the whole bar region and still being able to follow the evolution and formation of giant molecular clouds, we use the powerful hydrocode AREPO, coupled to a time-dependent chemical network, which is able to follow the major chemical species necessary to follow the thermal evolution of giant molecular clouds. We study the evolution of this car in an externally imposed BART potential. And the drawbacks of our simulations is that we don't have self-gravity, we don't have magnetic fields, and no stellar feedback. But still, the simple simulations that I will show are sufficient to actually explain the phenomenon that I want to explain with these in this talk. So we start with rotationally supported, fully symmetric initial conditions, and we start with the potential as fully symmetric, and we then turn the bar on gradually. So we see that slowly the gas settles into the shape that I just described before, having the external X1 orbits, the internal X2 disk, and the shocks that connect the tip of the bar to the central molecular zone of our simulations. And so if we take one of the snapshots in our simulations, we notice that the central molecular zone that builds up is formed by these large cloud complexes that follow X2 orbits. And we see already that we have a large degree of asymmetry in these kind of central molecular zone. So giant molecular cloud formation is surely one of the ingredients to explain the asymmetry. But certainly it's not the only ingredient, because, I mean, molecular clouds have typical sizes of a few parsecs, up to tens of parsecs, but they can certainly not explain asymmetries of scales of 100 parsecs. So the additional ingredient is actually the inflow of gas from these shocks. So we have, if you have noted from the previous simulations, there is episodic gas accretion onto the central molecular zone, which is disrupting these cloud complexes rotating inside the central molecular zone and enhancing their symmetry. So the other ingredient would be episodic gas accretion from the shocks, compacting and disrupting the clouds that are already inside the central molecular zone. But why do we have actually episodic gas accretion onto the central molecular zone? So it has been found that periodic shocks are hydrodynamically unstable, and this is exactly what is happening with the bar shocks in our Milky Way or in any barred galaxy. So this is in isothermal simulations, and you can see that the instability creates this vortices here, and these are the seeds in our 3D chemistry run to develop these clumps on the shocks that then flow down the shock to land on the central molecular zone and enhancing the asymmetry. To better understand what I'm actually talking about, let's select one of the cloud complexes inside CMZ, and we rewind time now. So this is where the gas that formed that cloud complex was about 40 mega years ago. So we see the major part of the central molecular zone was already formed, but there's a lot of gas that's coming in at later stages. So as the cloud complex rotates around the central molecular zone, we have these gas accretion from the shocks that compacts and disrupts the cloud complexes during the passage at the apocenter. Here is another cloud coming in. I think it's worth noticing as well that these things here, they are not single individual molecular clouds, but rather they are cloud complexes, an association of different molecular clouds. And while the center of mass of this stuff here follows an X2 orbit, individually and locally you experience a lot of complicated motions like rotations, shear, and cloud collisions, and so on and so forth. So if we look at the time evolution of the asymmetry, so here I show the degree of asymmetry as a function of time in our simulation. We see that it switches back and forth from a right-left asymmetry in at one time to a left-right asymmetry in another time. And if we look at the fraction of time that we experience a certain degree of asymmetry, so the Milky Way, which has 3/4 of the molecular gas coming from one side, would be here. We see that it is actually quite common to have an asymmetric central molecular zone, and we are in no special situation of the evolution of the center of the galaxy. So then we ask how would our simulation look, the central molecular zone of our simulation look like if we would observe it from the position of the sun. So here I plot the emission of the CO, which is actually this is the column density of the CO, and this is basically what we would observe. So we don't observe the molecular gas directly. And then we compare it to these LV observations. So here I show synthetic LV plot of our simulation, of the central molecular zone of our simulations. And if we highlight only the central molecular zone, we see that actually the asymmetry is reproduced both in longitude and in velocity. But not only, we also recover the larger scale gas flows. So this is a larger view from an angle of 12 degrees. So, for instance, we can highlight the galactic shocks that are also seen in our simulations, or, of course, the central molecular zone, but also secondary features like secondary dust lanes that are seen also in our simulations, or vertical features. We are preparing actually a paper on these as well. So that's an exciting topic and project to work on. And we are improving our models and currently running simulations with feedback and self-gravity. And with that, we can then address all kinds of different problems like star formation or formation evolution of individual molecular clouds and stuff like that. And with that, I come to my conclusions. And if there's one thing that I would like you to take away is the first point, which is the central molecular zone cannot be viewed as an isolated structure, but rather is part of a much bigger structure, which is the galactic bar. And to really understand the evolution of the central molecular zone, it's important to actually understand the connection of this gas to the outer parts of the galaxy. Then I've talked and tried to explain the central molecular zone asymmetry. And the ingredients necessary to explain the asymmetry is episodic gas accretion from the shock lanes and the molecular cloud formation themselves. Finally, I've shown that actually the CMZ is asymmetric, and it's quite common to have an asymmetric central molecular zone. And with that, I would like to conclude. Thank you. So I think that's kind of the figure 8, right? So that's so our simulations are 3D, but our galactic potential is concentrated on the mid plane. So it's actually and we don't have any kind of feedback or magnetic fields and so on. So it's actually kind of difficult to have this kind of up and down motion in our simulations. So we, I don't know where, okay. So we recover the kind of ring, but the up and down motions, these may be addressed in future studies when we include stuff like feedback or so on.
Also, is there potential point source?
No, the potential is the best fit of a Milky Way type potential. So it's a state-of-the-art Milky Way potential. So it's consistent with all the constraints that are there in literature.
Maybe you already talked about this and I kind of missed it, but is there like one thing that is responsible for controlling most of the gas accretion into the CMC? Is it like the material that the bar is like interacting with, or is it totally random?
So you mean how much of the material is in these shock lines that are then accreted onto? Yeah, that's a good question, and it's kind of difficult to address actually. So in our simulations, since the bar is actually turned on gradually, we lose a lot of angular momentum in the sense that we empty this region pretty fast. So we end up in the later stages of our simulations without gas here, and a way to replenish that would be, for instance, with a star formation or any kind of recycling mechanism.
One last question from the back.
Can you talk, so you mentioned these vertical streaks in the LV diagram. Can you talk a bit more about those?
Yes. So these feature in the observations, they are extremely broad in velocity. So they span about few hundreds in velocity, but very narrow in longitude. So we do see these kind of features in our simulations. So here there are not so many, but in other snapshots they are very, very evident. And in our simulations, these kind of features, they come from interaction of gas that is falling down these kind of shock lanes. So they have very high velocities. And for instance, gas that is here, that is has lower line of sight velocities, and the interaction creates these super high velocity dispersion features. Or for instance, gas that is overshooting here, that is coming inside the dust lane from this side here, has lower velocities than the gas that is flowing down this shock lane here. And when these two clouds interact, they form this kind of very broad features in the LV diagrams.
Right, so we have to move on, so let's thank Robin. Continuing on the same theme, I believe. Have Elizabeth Mills. Whenever you're ready.
All right. So I'm also going to be talking about the center of our galaxy, and I'm actually toward the end here going to try to start making comparisons with the center of another galaxy. Now, almost everything in this talk, I've been very, very careful to put things to scale in size. This slide is an exception because I'm lazy. So here, of course, one problem is these galaxy sizes are not to scale, and of course, they're not that close in the sky. Because one of them we live inside, and so the other problem here, of course, is we live inside this galaxy. We never can have this view of our own galaxy. So living inside of the galaxy, we are about 8 kiloparsecs, give or take, from the very central regions of our galaxy. And because of that, looking toward the center of our galaxy, you have to look through the disk of our galaxy to get to the very center. And this limits also the wavelengths that you use. So if you're trying to use optical wavelengths and look toward the center of our galaxy, you will essentially see a whole lot of nothing. So as I zoom in here, I'm going to be zooming in not just in size, but also going to longer wavelengths. So going to infrared wavelengths, where now you're piercing through most of the dust, and you can actually see that the center of our galaxy is a concentration of stars, hot gas, hot dust, right? A lot of activity. And zooming in further to the region that I want to talk about, the central molecular zone, around 300 parsecs end to end. And what you're seeing here is a 3-color composite, where the orange now is showing you the cold gas and dust. So each of those blobs is a giant molecular cloud and has something like 100,000 to 1 million solar masses of gas inside it. And of course, this is living in an environment of stars and clusters that have already formed, some of which are traced by the infrared in green, and some of which also are ionizing the gas, so making the purple emission, as well as various non-thermal emission, coming, for example, from the very center of our galaxy, around the supermassive black hole, Sagittarius star. So what I want to do now is start with a little bit of an accretion journey, because one of the things we're interested in, as was just mentioned by Robin, right, is how gas makes it into the center. So I want to give you an idea of just how long this journey is and the sort of scales you have to go through. So now I've switched back into right ascension declination, and we're going to be zooming in again toward the center, so toward the very central black hole. So the first step here is just a nice radio image. And so we're seeing, okay, there's a supernova remnant here. There may be a few forming stars in compact H2 regions, but the real activity is where the cross is. This is centered on our central supermassive black hole, Sagittarius star. So the next zoom gives you basically the stopping point right now for molecular gas. This is about as far in as this whole molecular gas reservoir. So the central molecular zone has maybe 10 million solar masses worth of gas. And about 10,000 solar masses of gas make it into this structure called the circumnuclear disk. So this is gas that's about, gas and dust, about a parsec away from the supermassive black hole. All right, everything beyond this, you're starting to look at gas that is either neutral or ionized. And you start seeing this, particularly this very, very hot dust here. So this is a forecast dust image. The hot dust is tracing a structure known as the mini-spiral. So you also see this in ionized gas. And so this is gas that's starting to make it a little bit closer to the black hole. A lot less of it, though. So even though that dust is very, very bright, the amount of gas that we believe is here in these ionized gas streams is about 30 solar masses. So you're talking about much, much smaller amounts of gas. Maybe as much as 300 solar masses in the neutral gas, neutral gas inside of the circumnuclear disk, but not much. So as you go in further, now you start being dominated by stars. So you get into the central light year here. And one more zoom takes you into now the stars that are used to determine the mass and tell us that there is a central supermassive black hole. And so these stars are about 0.03 parsecs away from the black hole. And they're so close to it, of course, that you can actually see their motion. As you watch them for dozens of years, you can actually see them going around. Now, one last zoom just for fun, because of course this is something we're all waiting for eagerly. But you might want to ask, okay, so the gas has made it this far. How far does it have to go to actually get to the supermassive black hole? So the type of simulation of what we hope to see soon from the Event Horizon Telescope, note that this is, we've gone from 0.03 parsecs for the star cluster down to that 6 zeros, 0.0000002 parsecs, right? So an extreme journey, many orders of magnitude that the gas has to take. And one of the things that's most interesting, right, is asking exactly how far does this gas go, for example, to do things like form stars. So everyone's here for the star formation, so I want to give a little sidebar. Where is the star formation happening on all of these scales, right? So is it forming stars? Where are those stars? So the first scale that I want to talk about is the very center here. So this is Sagittarius B2. This is about 100 parsecs away from the black hole? And here the answer is yes, thumbs up. It is forming stars. In fact, presently we believe. So we see hot cores, for example. So this is an example of yes, we are forming stars. You can go a little bit closer to the supermassive black hole. Now we're maybe 30 to 40 parsecs away. Now, of course, we don't know exactly where they formed. And you see clusters that formed anywhere from 3 to 6 million years ago, right? Very massive star clusters. So we see evidence of past star formation. And then we ask, okay, now when we're zooming in, what else do we see? So if we zoom into 7 parsec scales, as I noted before, we see these sort of compact H2 regions. So this is nice. This looks like maybe star formation within the past, say, 100,000 years. Just one problem. If you believe current models, for example, from Dietrich Kreuzen, even though these look like they're maybe a few parsecs away from the black hole, current models actually put these as much as 50 parsecs in front of the black hole. So that's recent star formation, but it's not actually star formation that close to the black hole. You can go a little bit further and ask, is the circumnuclear disk forming stars? I will just say no, right? There's some controversy here, but at this point, our best evidence for how dense the gas is and things that unambiguously trace star formation suggest that there is not active star formation in this structure. And you can keep on zooming in a little bit. Definitely no, right? There's really not enough gas in the mini-spiral, and it's all ionized and neutral, so we don't really think that that's forming stars. And then we get to another yes, but again, a long time ago. So the S stars, for example. These are interesting because we believe they formed actually where they are right now, right? Only 0.03, 0.05 parsecs away from the black hole. And so this cluster actually shows that you actually have to you can take gas all the way that far in, right? And form stars, even though at this point, right, this is as far as we've gotten stars right now. Of course, you can ask, no star formation there. Focusing on those S stars, because they are really interesting, the central nuclear young cluster here. This is the only clear evidence that we have in the galactic center of star formation actually being weird, because maybe the conditions themselves are, in fact, as we know, the gas conditions are quite weird. So here, again, the stars that formed 0.03 parsecs away from the black hole, here you actually see evidence for a top-heavy IMF. And the reason I say this is our best evidence right now is because these stars mostly formed in the potential of a supermassive black hole, and for the most part likely stayed there. Whereas when we measure the IMF, or rather the present-day mass function of the other clusters, it's very likely that they've been stripped significantly by their journey throughout the central potential. So here we say, okay, stars that close to the black hole seem to have formed differently. So one question is why? And of course, sort of qualitatively, I'll say, okay, you're really close to a black hole, things are going to be freaking weird, but what exactly is going on? So in general, in the galactic center, the gas is at least 1 order of magnitude more extreme than we see elsewhere in the galaxy. So it's about an order of magnitude hotter, up to 200 Kelvin, compared to the sort of 10 to 20 Kelvin you see in the gas elsewhere in the disk of our galaxy. Also, on average, much more dense because it is packed into a very small region. So you've got average densities, about 10 to the 4th molecules per centimeter cubed. Average densities in the disk, about 100 molecules per centimeter cubed. And then, of course, it is much more turbulent. So on these sort of cloud scales, you see line widths 10 plus kilometers per second, where you might see a few, and other infrared dark clouds. And so one question is, okay, this is plenty weird, but we don't yet have evidence that this amount of weirdness forms stars with a differing IMF. What happens as you actually go close in? So now as we go as close in as the circumnuclear disk, do we actually start seeing evidence that the gas is significantly more extreme, perhaps in a way that would help us to understand how much more extreme the stars are that formed closer? So to do this now, so this is work with an old telescope, so you have to go back in the day a little bit. So this is the ISO satellite doing far infrared observations, because these are observations actually of H2, molecular hydrogen. The thing that we all want to know what it's doing, but in most environments, they're too cold for us to actually see substantial emission directly from rotational lines of H2. Nice thing about the galactic center, it's hot, right? So here you actually get a significant population in these H2 lines. And so here I'm showing you isospectra in these boxes toward 3 positions of the C and D. These are spectra of pure rotational H2 towards the southern region. We don't detect the S0 line, the lowest line, but we make up for it by detecting everything up to S13. So very highly excited lines of pure rotationally excited hydrogen. And you can use this to measure the temperature of the gas and also measure the mass of the gas, but that's another story. So focusing on the temperature, so you can count up, right, the number of molecules that you see in each of those different energy transitions, plot the column density, here normalized, against the energy of that transition. It's called a Boltzmann plot, and it lets you know something about the temperature of the gas. If there's a straight line on this plot, generally that tells you single temperature component. Curvature, you start to ask yourself, okay, are there actually multiple temperatures present? What we did is we said, okay, we see curvature, and we actually want to describe this maybe a little more physically than has been done, not by saying there are 1 or 2 temperature components, but a continuum of temperatures. So what we do is we fit this with a power law where we essentially say that at each temperature, there's an amount of gas at that temperature proportional to the temperature to some exponent, right? So T to the minus N. So that power law exponent, what that tells you, if N is small, that means you have a flat slope. More gas at high temperatures relative to low, compared to a steep N or a large N, in which case you have less gas at high temperatures compared to low. And what's interesting is we see very clearly toward the circumnuclear disk a power law index of about 2.8 that's significantly lower than the power law index you see toward other galactic center molecular clouds. So we see evidence that in this gas that's within a parsec away from the black hole, you actually see temperatures that are much more hot gas relative to the amount of cool gas. So elevated temperatures. So you can ask why, right? So what's going on that's making this gas hotter? So this gas doesn't seem to be radially excited. It seems to be collisionally excited. Another interesting thing going on is the line widths in the circumnuclear disk are very broad compared to other regions in the galactic center. So there's been nice work, for example, by Katha Immer, who's been showing that there seems to be a correlation between line width and temperature in the galactic center, suggesting that turbulence is the #1 thing doing the heating. And so what we're saying here is this seems to be starting to tell us a story where as gas gets further into the center of the galaxy, it gets more turbulent and it gets hotter, right? And if you're seeing this sort of radial dependence, that maybe suggests that actually the fundamental place that this energy and the turbulent energy is coming from is actually from gas just falling into the potential of our galaxy. Because our black hole is not an AGN, and there's not much star formation going on in our galaxy. There's not much in the galactic center. There's not much that would be causing feedback type processes or other things that might be heating. This seems to be sort of a passive heating where it's a story of just getting gas to the center of a galaxy already uniquely changes it compared to the rest of the galaxy. So now we want to ask, okay, so that was our galactic center, super nice case study, right? Really close by, really easy to see what's going on in detail. Now you want to start comparing it to more extreme things. You want to have a sample size larger than 1 to look at galaxies where maybe actually something, anything is happening, right? So one option is NGC 253. It's about 3.5 megaparsecs away. It also does not seem to have an AGN, but what it does have is a nuclear starburst. So it does have in the central regions about an order of magnitude more gas, and about an order of magnitude higher star formation, at least. So it's producing something like 3 solar masses a year, whereas our galaxy is producing maybe less than 0.1, right? So not much star formation. So this is a nuclear starburst, and so we want to ask now, how are conditions changing here, right? How are conditions changing relative to sort of the baseline that we've established for the center of our galaxy? So this is all a work in progress, but I want to show you some of the nice new ALMA data here. So first, again, we have to always zoom in. So zoom in on the nucleus of the galaxy. So here's a Hubble view now. Zooming in a little bit further, you can start to see the central starburst actually just at optical and infrared wavelengths. So you can see each of those dots is now a super star cluster, essentially, that is forming there. And you're starting to see, okay, so this black bar is about half the size of our central molecular zone. So we can zoom in on this and examine the starburst in really nice gory detail. But now, of course, what we want to know is where is the gas, right? Where is the fuel for this starburst? Where is it located? So these are ALMA images from working with Alberto Bellato and Adam Leroy. So these are our new long baseline. This is band 7, so HCN 4 to 3. And here we're getting down to spatial scales of about 2 parsecs. So about 2 parsec spatial resolution, looking at what the gas is doing here. So we can compare this to a really nice map that was made by Kunihiko Tanaka. Exact same line, slightly higher resolution in the center of our galaxy. And we can actually start making what I'm really excited about, which is this apples to apples comparison, right? Same lines, same resolution, same region, and start asking what's going on. Already you can see one of the big differences in the black contours here, which are radio continuum, which is that here, it's a starburst, as we expect, right? Basically every cloud here has a forming, likely, cluster / supercluster going on inside of it, right? So almost every cloud here really appears like it is forming stars like gangbusters. Whereas here, basically, the only place that would be happening is Sag B2. One of the really nice things when you start to ask what is actually setting, right, the scales of everything happening, is to look not just at the size scale, which again is a gorgeous match, but also at the velocity structure of these two. And so here you can see, so here's sort of the same sort of image of the same size scale, but now I'm showing you a position velocity plot. And again, in both of these, NGC 253 is also a barred galaxy. You see a nice tilt here and also a separation in the velocity, which is suggesting, again, this same sort of ring or stream features that are going on. Main difference that we see so far is certainly a broader line width in NGC 253. But we've not looked carefully to see to what extent that's a broader line within the few clouds that are not as actively star forming, and to what extent this is actually a broader line width because something, potentially these clusters, is in fact launching a molecular wind from the disk of NGC 253. So going forward, so what we're really interested in, two things, again, really sort of understanding how the center of our galaxy, what sets the conditions here, and to what extent this is a nice example of initial conditions without feedback effects. So gas is extreme simply by virtue of getting the journey, getting to the center of the galaxy, and not necessarily because of what it encounters there. And then using this to start make really nice comparisons and start isolating, right, now just the effects of feedback. So again, a nice sample that says we're still not worrying about AGN, but starting to understand just how stars and stellar feedback are now changing the gas properties in addition to what we find in the center of our galaxy. Thank you.
For a couple of quick questions.
Yeah, this is very interesting to do this kind of comparison. It should be done for more galaxies, I think. One question I had is you said that 253 was a starburst, yet 2.8 solar masses per year is kind of low for what I thought a starburst was. Is that only from the nuclear?
Exactly, yes, so apologies. So that is specifically for the inner, I think, around kiloparsec, so the nuclear starburst.
How does that compare to the overall stuff?
That I don't know. I believe that the center is much more active than the rest of the galaxy, but I don't know exactly what the rest of the galaxy contributes.
Sandra, you can set up.
If someone else has a question, I just wanted to ask, I don't know what HCN trace is.
Good question. Meme question. Yeah, so I mean, nominally HCN traces somewhat denser gas than you see with CO. But in general, it's found pretty ubiquitously, as in our paper, even at relatively low columns toward the galactic center. So it seems to be quite extended. So in general, it seems to be a pretty good tracer of just gas that is in the galactic center, not necessarily the densest gas that is in the galactic center.
Let's thank Elizabeth again. Right, and next up we have Sandra giving a framing talk on star formation on larger scales.
Okay, so hi everyone. I think this is the first conference where I signed up to not give a talk and then was awarded a large part of a talk, and which I'm of course very, very thankful and very appreciate the opportunity. So I will be really zooming out and you know, the framing talk is about cosmological scales, so I will be talking a lot on kind of the cosmic star formation and density and so on. But a large part of my research is really trying to understand how galaxies grow on spatially resolved scales, and this is of course, you know, part of how the star formation rate is distributed in galaxies on spatially resolved scales. And so, you know, a lot of data I'm working with is coming actually from the Hubble Space Telescope. We can now really zoom in on individual galaxies that, you know, had formed most of the stars at the key epoch of redshift of about 2. So you can imagine that this galaxy now, has emitted its light 10 billion years ago. And now we are able to really get this light and start analyzing not only what we obtain with HSD, but also with ground-based VLT symphony adaptive optics observation, where we can get a handle on the H-alpha distribution in these galaxies and therefore get a handle on the star formation distribution. So just a brief outline of the talk. So I will be very brief at the beginning to talk about how we measure star formation rates in galaxies, so that we just are on the same page. And then I will talk about the cosmic star formation rate density and how this links to the overall dark matter halo growth in the universe. Then I will be talking about quenching, so when you stop forming stars in galaxies, and then I will end up with some spatially solved properties of galaxies at redshift of 2. So we can describe the luminosity of a galaxy at a certain wavelength and time, by this very simple equation where we just have the evolutionary tracks of stars, the star formation rate, as well as the IMF. And so one of the key things we want to measure is, of course, the star formation rates. And so one can do this when we measure, the luminosity at different wavelengths and then do kind of a modeling. So there are two ways. One is a modeling, simple SED fitting. And the problem there is, of course, that it's very hard to cover all the parameter space. I must say that here with Charlie Conroy's research group, there is a lot of ongoing research in that to improve star formation estimates from the SED modeling that don't depend too much, or at least we kind of understand how they depend on the input of stuff like the IMF or the stellar tracks. Another way, and most commonly used, is actually simple recipes where one just converts the luminosity measured in a certain band to the star formation rate. And so what one assumes is that the star formation rate is constant over a certain time scale. And this time scale is usually of the order of, of 10 to the 8 years. And so then actually, when you can, do a simple example with the UV light, you can see here, this is the luminosity in the UV over the star formation rate. And you can see that, when you have a constant star formation rate, that you are approaching a certain asymptotic conversion factor. And this is just because the O stars are kind of leaving, the main sequence of stellar evolution. And so you can use this to convert then the UV luminosity you see in a certain band to convert to a star formation rate. Now, the problem, of course, there are a lot of dependencies that are kind of hidden, from metallicity to aging, IMF. But the largest uncertainty is, of course, the dust correction. And so dust, at least in extragalactic studies, are treated in a very simple way. Usually, one has a so-called recipe for attenuation. This is just, a wavelength dependent recipe to convert or to correct for dust attenuation. And you have to imagine this encapsulates all kind of weird effects, such as dust geometry, so how the stars and the gas are distributed in the system, as well as the extinction law itself and scattering. So we encapsulate everything in this simple law. And so when you measure then, for example, the color far UV minus near UV, so you get a handle on the UV continuum slope, which is usually described with beta, you can then go and say, okay, how much dust correction do you need to apply based on this simple color? You can see the problem here, that there are many different extinction laws one can use, and therefore one can get a large variation of how much dust correction needs to be applied. One way to solve this is actually to go to the infrared, so one can use UV plus infrared star formation rates. This seems to be nice because the UV light gets absorbed and re-emitted in the infrared. But again, there are problems there. I just mentioned briefly HGN as well as dust heating by older stellar populations that can complicate this conversion significantly. Then another nice way to measure star formation rates is coming from recombination lines, such as from hydrogen H-alpha. Again, H-alpha is much redder than the UV, and so we have overall less dust obscuration. But again, because actually these recombination lines are coming from H2 regions that are probably embedded within some H1 clouds, there is some extra attenuation towards these regions. And so, there is another uncertainty that one has to fold in when one wants to correct the H-alpha emission line for the dust attenuation. And finally, there are other star formation rate traits, such as radiant X-ray, which I will not be covering really in this talk. In any case, so nowadays we have measured the star formation rates, in deep surveys for many, many galaxies. And so we have now a very good understanding of how the cosmic star formation rate density, so the solar masses per year per Kumho megaparsec, how this evolves as a function of redshift or look-back time. And so when you look at the UV as well as the infrared measurements, just to mention, the UV now again, are probably the very high redshift regimes. There, all the dust correction have been done with the UV continuum slope to keep in mind. But we see that overall there is good agreement, and so we can, really trust that there was a decline at early times, and then it is increase and peak at redshift of about 2. And so you can imagine that, between these redshifts, 1 and 3, you form about 50% of the total stellar mass in the universe. So a significant amount of stellar mass that we see today in galaxies have really formed at this epoch of about redshift of 2. Now, when you see this simple curve, you want to, of course, understand what is the physical driver for this increase at early times, the peak at redshift of 2, and the decrease at lower redshifts from redshift 2 to today. And so a simple way to model galaxies, we have seen galaxies are very complicated. We have really zoomed in on great details on how the stars' individual molecular clouds are forming. I try to give you now a bit of another picture coming on from the larger scales. And so actually, John Forbes is one of the experts here, discussing kind of the self-regulation of star formation in galaxies. So we can think of a very simple picture where we have a dark matter halo. We have a galaxy, which consists of gas and stars. And you're converting gas into stars at some rate. And so we can write the star formation rate to be the gas mass divided by some star formation time scale, sometimes also called the depletion time. We can then have some accretion of gas, that falls into this regime. And then we have also some outflowing gas, And so we can then write simply the outflow rate to be proportional to the star formation rate, because we think that the star formation rate or the star formation actually drives some of these winds. And when we do this, we can just write the simple balance of the gas mass. So, there is accretion, there is star formation rate, and outflow rate. And so we can find a very simple solution, actually, especially in the regime where the changes in accretion rates are on longer timescales than the star formation rate. So if the regulator can really react on short timescales in comparison with the change in accretion rate, then we actually go into a regime where we have a steady state solution where the star formation rate is just proportional to the accretion rate of this system. Now, this can be used, and John has done a lot of work in that for understanding how metallicity evolve in galaxies. I will be focusing now on a simple model to kind of show you how one can explain the evolution of the cosmic star formation rate density as a function of cosmic time. So what I show you here are just, as a function of time, how the dark matter halos kind of grow up. So they merge, and so we have the question, of course, how do you populate these dark matter halos with galaxies or with star formation rate? And so when we have this picture in mind, so the star formation is just proportional to the accretion rate, we can think of, okay, let's try this approach where we write the star formation rate of a given dark matter halo at a given redshift to be some efficiency of converting the dark matter accretion rate or the gas accretion rate to stars times the accretion rate itself. And so here one can then approximate the accretion rate by the halo mass divided by 2 times the assembly time. The assembly time just tells you when a certain halo mass reached half of its initial mass. And so you can see that this can be rather easily obtained from extended projector formalism. So this is all analytical. You can also go to cosmological simulations. It doesn't really matter. The key point is that we have here an efficiency that is redshift independent, and we can obtain this efficiency by simple abundance matching at redshift 4, where we just say that the halo that is the most massive one also has the highest star formation rate. And so if we do this, this is the result. So we actually are able to reproduce with this very simple model the cosmic star formation density as a function of redshift. And of course, the question is, what are the key drivers? So at early times, it's an effect of that you have more and more galaxies that are able to host star-forming galaxies that are able to form stars efficiently. And then there is a peak where there is a decrease, and this is because there's a whole less accretion onto individual halos, but also in some halos, the galaxies are actually switching off their star formation. And so the key figure or the key thing to take away is that we can understand the evolution of the cosmic star formation rate density without invoking any redshift-dependent efficiency in converting gas into stars. Now, I will just, explain a bit more on what I really mean with this. So, when we look at the efficiency, so this is really telling you, the star formation divided by the dark matter halo accretion rate. As a function of halo mass, we have this shape here. This is quite familiar to people who, when you look at, for example, the halo mass function divided by the stellar mass function, it looks very similar. It peaks at redshift of it peaks about at the mass of 10 to the 12 solar masses, and so this means that these halos are actually hosting the galaxies that are forming stars most efficiently per a dark matter halo accretion rate. Now, at early times, you can think of, okay, how does the halo mass function evolve? You can see that, at early times, m star is kind of below 10 to the 12, and then evolves like this to redshift 0. So you can see that, when you look at 10 to the 12, you can see that there are more and more galaxies populating this regime where you are able to form stars very efficiently. And then at the high masses, at low redshifts, you're increasing this part here, but there, you have galaxies that are not able to form stars any more efficiently. And so this explains you going up, when you go from lower and from high redshifts to the peak. This is really just this increase you can see here. Now this is, the model I showed you is very, very simple. But I just want to show you here there are more complicated models that, introduce a lot of, like subhalo abundance matching and so on. They're, much more complicated models, but they come to the same conclusion. This is halo mass as a function of time since Big Bang or redshift. You can see that, again, when they look at the efficiency, star formation by the mass accretion rate, this is very constant as a function of redshift. Okay, so this 10 to the 12 solar mass halos are really the halos that host these galaxies that form stars most efficiently. And so just, to highlight now again, this is what I just mentioned before. This is when you look at the dark matter halo mass function, look at the luminosity function or the galaxy stellar mass function. This is exactly telling you that there is some, some inefficiency down here and some inefficiency up here. And the inefficiency at lower masses can be understood mostly by stellar feedback. So, this is supernova as well as winds. Whereas at high masses, there is still, I think, a very big question mark. A lot of people talk about halo mass effects, HEN effects that kind of play together, but also some people would say there are internal effects to really make galaxies less efficient in forming stars when they reach these high halo masses. And so, this is one of the big open questions still in galaxy evolution. So, trying to understand a bit more how galaxies themselves evolve. We have already heard from Charlie yesterday that there is this so-called star formation stellar mass relation, also the star forming main sequence, which shows that there is a correlation between the star formation rate of a galaxy and the total stellar mass. You can see that this relation goes up to very high redshift. This is one of the early works of 2007. So today we can probe this up to a redshift of 3 or 4. And it seems that this relation is roughly linear and has a scatter of about 0.3 dex. And the scatter seems to be rather constant as a function of redshift as well as stellar mass. And it has been used to say that the star formation histories cannot be too arbitrary, meaning that there are not too many starburst systems in the universe. And this indicates again that there is some kind of self-regulated growth on some kind of longer timescales, and you cannot have very, very large starbursty system because otherwise you would overshoot or you will have a much broader scatter in this relation. It seems that the star formation rate, the main sequence is higher at high redshift. So when you look at the given mass today, you think, okay, typical, Milky Way-like galaxies forming maybe a few solar masses stars per year. At redshift 2, this were maybe 100 solar masses per year. So there is a significant increase in the star formation rate at the given stellar mass. At all epochs, we can see that there are galaxies that are significantly below the star forming main sequence, sometimes called quiescent or quenched galaxies. And again, this is linking directly to the picture before. At certain halo masses, at the highest masses, you are kind of shooting down galaxies, and you can do a better calculation of how many there are. Is when you look at the number density. So this is the number density as a function of stellar mass. This is from redshift 2, redshift 1, and redshift 0. You can see that at early times there were many star-forming galaxies and only very few quiescent galaxies. Now, I told you the star-forming galaxies, they're forming stars roughly linear to their mass, and so you would expect that, all of these galaxies are increasing their mass. So, you would expect that at the later epoch, the mass function should look something like this. Now, when you look at redshift 1, you can see that indeed this is the case for a low mass end. There are, many more objects down here. But at the high mass end, you see that the turnover, so the m star of the Schechter mass function stays roughly the constant. Okay? And so already from looking at the star-forming population, you would infer that there must be galaxies dying or, switching off their star formation around this mass scale. And indeed, when you look at the quiescent galaxy population, you see that there is a significant increase in the quiescent population around this mass scale of roughly 10 to the 11 solar masses. So this has been, called, quenching, so really the switch off of star formation. And when we go to lower redshifts, we can see that, at high masses, there's not much evolution anymore, but what you can see is a significant increase in the quiescent population at the lowest masses. And this is, when we look into SDSS, we can find that this is mainly because there are more and more satellite galaxies that are switching off their star formation. And so they have been invoked, at least from an observational perspective, that we have a quenching at M star, so at around 10 to 11, and a quenching at low masses. But this is just, to say that, well, we know how it seems to evolve as a function of redshift and mass, but physical mechanisms are still, a large question mark. Then, of course, when we look at today's universe, it seems, very, since Hubble, we kind of know that, okay, the quiescent galaxies, they look like early type galaxies, so they have this kind of morphology, whereas the star-forming galaxies are dominated by spiral galaxies. Now, when we look at redshift 0, we still think, oh, yeah, we have to make from, we have to kind of convert these galaxies to those galaxies. But I think when you look at this diagram, you can see that, well, actually what we want to make is these galaxies at earlier times. Because especially when you look at the massive galaxies that are around 10 to the 11 solar masses, most of those galaxies have actually formed in a redshift of 2. So if you want to understand the formation of early type galaxies, in particular massive early type galaxies, we need to go back in cosmic time to look at star-forming galaxies at redshift of 2 or so. So looking at some scaling relations, so we discussed this actually in our on-conference session today. So it has been now measured rather well. I mean, the problem is, of course, conversion factors. I don't go into the details. How do you convert the CO luminosity to a gas mass as well as, or a kind of dust continuum flux? But if we take now measurements that have been done by different groups, we see that the depletion time actually varies only very weakly as a function of redshift. So it is actually rather constant. You can see it goes as 1 plus 10 to the power of minus 6. What varies a lot, on the other hand, is the gas fraction. So we can see that the gas fraction evolves significantly from redshift 0 to redshift 3. It goes as roughly 1 plus 10 to the power of 2.8. And when you remember before, the redshift evolution for the main sequence is also going very similarly. And so the main thought is that the main sequence, so the star formation as a function of stellar mass relation, is evolving significantly as a function of redshift because you're having more and more gas at higher redshifts in these systems. I think quite interesting is that we are now able also to trace actually the properties as a function of the scatter. So we can look at the star formation stellar mass relation color-coded by the depletion time, and there is a gradient for the depletion time as well as the gas to stellar mass ratio as a function of whether you are above or below the main sequence. And so this should also tell you something on the self-regulated nature of how galaxies grow their stellar mass as a function of redshift. So very briefly about kinematics. So what I'll show you here is a typical redshift 2 galaxy in HSD. This is showing you the same galaxy with infrared adaptive optics. And so you can see the H-alpha emission line flux distribution as well as the kinematics. And so we are now really able to start understanding what the kinematics of these systems are. Now we talk here still of kiloparsec resolution. Okay, so some of you must be disappointed, but this is pretty cool. The problem, of course, is because adaptive optics is still very expensive. You have to think of integration times at the VLT of the order of 10 hours or more. So we can only get of the order of 30 galaxies. The nice thing is there is also KMOS. The problem there is the resolution is much lower. We talk here of 5 kiloparsec resolution, but they have multiplexing capabilities, so you can observe of roughly 30 galaxies in one shot. So you have, you can do much higher number statistics. So the picture people from there are presenting is that the dispersion as a function of redshift is increasing. And so it seems that, when you look at at least, this is, just keep in mind, this is all ionized gas kinematics, so not stars. But it seems that, that the dispersion is increasing. And one way to understand this, when you look at the tumor stability criterion, V rod over sigma, you can express this as, when you think of putting Q critical to 1, so, marginally stable disk, you have more or less the evolution of the gas fraction, what is kind of reproduced as V rod over sigma. And so these kind of simple models are able, it seems, to produce such trends that indeed the gas fractions are driving some of these higher velocity dispersions we see in these early galaxies. Okay, so now I'm kind of addressing some of the questions that I've been working on the last years and kind of linked to the slides I've shown you until now. Maybe you should tell me how much time I have still. Okay. So one thing is that when we have, so for example, the star forming main sequence, so the relation between the star formation rate and the stellar mass. It is interesting to understand what really the physical processes are that confine these galaxies to such a narrow main sequence, because it tells us also a lot about how galaxies may evolve along such a sequence. The problem in galaxy evolution that we are facing is that we see a lot of scaling relations, from low redshifts to high redshifts, but it's not clear whether individual galaxies are actually, following these trends. Okay, and the one way to go for is to understand maybe the scattering these relations better. We can imagine that if a galaxy always stays, above a certain scaling relation, then of course its average evolution with time doesn't follow the average of the whole population. And so it links all at the end to asking the question of how diverse are star formation histories. And so there, I think we still have a good understanding of how scaling relations evolve as time, but we don't know well how individual galaxies are evolving along these scaling relations. Another, did I just change there are too many of these. Okay. Another question is about the spatially resolved stellar mass growth in galaxies, and of course this links directly to the star formation distribution, and then also how do galaxies really stop forming their stars on spatially resolved scales. And so I'm just very briefly talking about simulations. So this is the cosmological zoom-in simulation of Vila. There will be more on simulations from Benedict afterwards. So these are a few simulations where we are able to really follow, the whole cosmological box, let's say, and then zoom in on a few individual cases of the order of 26 galaxies. We probe halo masses between 10 to the 11 and 10 to the 12 solar masses, and we have stellar masses between 10 to the 9 and 10 to the 11 solar masses. So these are, quite massive galaxies. The nice thing is, in such simulations, you're able to really, resolve down to 25 parsecs, which doesn't sound great for you, but for us, it is actually, it's very nice, because then we can start understanding how, how stellar mass is forming on, let's say, at least the kiloparsec scale quite well. So there's an implementation of thermal radiative feedback from stellar winds and supernova, but important to mention is that there is no HEN feedback implemented. And so, of course, the nice thing in simulations is that we can really go and see how individual galaxies evolve. And so we can look, for example, at figures such as, the distance from the star-forming main sequence as a function of the total mass. And we can follow how individual galaxies evolve along such a main sequence, okay, which we cannot do in observations. And so here I show you just 8 example galaxies. And what you can see is that, indeed, galaxies are evolving up and down the star-forming main sequence as a function of time. And so just, yeah. What I show you as well is that, the gray line here shows you when the galaxy's halo is reaching a halo mass of 10 to the 11.5 solar masses, which is a mass where there is a viral shock usually developing in the halo, and the gas accretion onto the system drops. And so you can see that, indeed, galaxies usually fall below the main sequence after this halo mass. Now, what I've color-coded it by is the central gas density. And so what you can see, at least here in a weak trend, is that the galaxies at the upper envelope of the main sequence have a higher central gas densities than galaxies below. And so this is something actually we discussed in the working group or in the unconferenced session. And we can find similar trends, for example, with the gas to stellar mass ratio as well as the depletion times. And so we can measure these trends and then compare with observations. And this is what I show you here. This is the gas to stellar mass ratio, depletion time as a function of the distance from the main sequence, so along this axis. And so we find shorter depletion times for galaxies at the upper envelope of the main sequence and higher gas to stellar mass ratios for galaxies at the upper envelope of the main sequence. And you can see the red dashed line shows you what observations give us, and it seems to reproduce what we see in the simulations very well. So this speaks for some kind of self-regulation, at least on timescales of 10 to the 8 years. So the picture that develops is exactly that galaxies are moving up and down, and so the simple view is that we have in these galaxies at redshift of 3, we have gas fractions of up to 50%. So these are very gas-rich galaxies that have some rotation, but then you have a small disturber. It can be a merger, but it's already enough to have a counter-rotating stream that is lower the angular momentum of the gas disk and drives a lot of gas into the central region. And so you are building up a gas surface density in the central core. You're really building up a lot of gas in the central part. And because of that, you're forming stars very efficiently. So the specific star formational profile is suddenly increasing in the central part. So you're building up a dense bulge component. Because of stellar feedback, then you're turning around. So there is the gas, that produces stars, and the stars themselves have then, winds that want to shut down the star formation in the galaxy. But at these early epochs, we have that the replenishment time of the gas is very short in comparison with the depletion time. So the gas gets, reaccreted, and so what you're ending up with is it's kind of a star-forming ring-like configuration where you have a lot of gas in the outskirts. And so you can go through such phases several times until you reach a halo mass where then the accretion rate onto the galaxy is not catching up anymore with the depletion time. And so, of course, we want to go in observations. I have to accelerate, I think, a little bit. But the key observation program that we have put together from MPE at ETH Zurich as well as in Padua is combining a large VLT Symphony adaptive optics program with Hubble Space Telescope imaging, where we try to cover a wide range in stellar mass and star formation rates for galaxies in order to really kind of pin down the internal workings on kiloparsec scales for these galaxies. And so we have, for a sample of about 30 galaxies, the kinematics, the stellar mass density, the star formation rate density, and the dust attenuation on 1 to 2 kiloparsecs. Okay, and so this is kind of the state of the art without lensing. And so what I show you here are dust attenuation profiles. This is really coming from the far UV minus near UV color. And so you can see that there's a lot of diversity in individual galaxies. So I show you here 10 individual galaxies. And so you can see some galaxies have really a lot of dust in the central part, whereas some galaxies have a declining curve into the central region. Now again, this is, it's very simplistic. It's just far UV minus near UV color, and so we assume a foreground dust screen and a Calzetti-like extinction law. So these things are very crude, but honestly, it has not been really taken into account for many of the high redshift observations that there are dust gradients in galaxies, and of course they're very important because usually the central part is more dust obscured than the outskirts. And so if you want to understand how galaxies are growing, we can look at the specific star formation rate profiles. So this is really the star formation rate surface density between the stellar mass surface density. And so you can see that lower mass meaning between 10 to the 10 and 10 to the 11 solar masses, we have roughly flat specific star formation rate profiles. And so this means that you're doubling your mass in the central core and the outskirts, hand in hand. And so we can, compute a timescale that is roughly 300 million years. So, these massive galaxies are doubling their mass every 300 million years, both on average in the center and in the outskirts. On the other hand, when we go to more massive systems, of the order of 10 to the 11 solar masses, we actually see that the specific star formation rate is dropping in the central core. And so when you are now interested in understanding, the growth rates, we see that the mass doubling timescales are longer than the Hubble time. And so these galaxies are still forming stars, but they do this at a rate that is not very significant anymore in comparison with the stellar mass that is already in place. And so we can do this, a bit more on, splitting up by stellar mass and star formation surface density profiles shown in blue and red. And so, when you focus first on the high mass, you see that the stellar mass densities are very high in the central core. So we have stellar mass densities that are comparable to local early type galaxies. And so these galaxies, have star formation rate in the center, usually in a disk-like profile, but the stars you're making it, with these rates are insignificant in comparison with the mass that is already in place. And so we can, what we can do is we can spatially understand how the galaxies have to stop forming their stars. So we can look at the stellar mass surface densities we measured at redshift 2 and compare it to local massive early type galaxies at redshift 0. And so we can understand, we can build a simple model and see, okay, how do we have to switch off the star formation on spatially resolved scales? And so we see that this has, at least from our data, to happen from the inside out. And so we can compute timescales for this. It's of the order of a few 100 million years in the central part, but it can, the star formation can take on for, another 1 or 2 gigayears in the outskirts without violating the stellar mass surface densities we see in local early type galaxies. Now, the problem is, of course, these are observational signatures, and it's very hard to go from an observed correlation or an observed signature to some physics. And there have been many mechanisms being proposed to switch off the star formation in galaxies. And it's really hard from such observations to say, oh yeah, it has to be this, because most of these things act together and also produce actually very similar observables. And so maybe one thing I want to mention is that, concerning HEN-driven outflows, is that when we look into with our data into the H-alpha emission line, we can decompose the lines into narrow and broad components. And so what I show you here are, the contours show you the broad H-alpha component, and the green shows you the narrow H-alpha component. And so you can see that when you go to the central region of these galaxies, there is more and more broad component. And we can, plot this here maybe a bit better. This is the full width half maximum of the broad component in the disk and the nucleus. And you see when you go to higher and higher mass objects, the nucleus, the broad component nucleus, gets more and more significant. And we measure velocities of the order of 1,500 kilometers per second in the central core, whereas in the disk part, so in the outskirts of these galaxies, we don't measure these high velocities. In addition, we can look into N2 over H-alpha ratio, which is an indication for HEN or shock-like features, and we see that there is an increase from N2 over H-alpha when we go to these more massive systems. So I think now I quickly skip over this part, and well, maybe I can mention that so I showed you before the specific star formation rate profiles for galaxies that are in the quenching regime in the simulations. When we do now a mass match sample from the simulations to our observations, we actually observe a very similar shape, which is showing you that, well, even in simulations where we don't have an HEN, we can still reproduce the same signature. And so this just highlights to you that, even though we measure certain trends, specifically about a specific star formation in simulations, it's still hard to prove what kind of quenching mechanisms have to be at work. Okay, so coming to the conclusions. So concerning the overall picture, so the cosmic star formation rate density in the universe, it is quite clear that a simple model where we just have some efficiency that is redshift independent can actually reproduce the overall cosmic star formation rate density, and this is mainly because of the buildup of how dark matter takes place in this lambda CDM universe. A key thing is, if we want to understand how galaxies evolve, I think, is that we have to take into account higher redshifts, and in particular, the redshift 0 galaxies and redshift 1 or 2 galaxies are very different. So we can look at typical star-forming galaxies at different epochs, and what I'll show you is that there is a lot of differences between these populations. And this is, of course, important if we want to understand how galaxies stop forming their stars. We shouldn't just compare redshift 0 populations. We should actually go into high redshift galaxies to really understand how we can link progenitors and descendants across cosmic time. Then I have showed you some results on star-forming galaxies above redshift 2. We see that below a 10 to the 11 solar mass galaxy, we see on average roughly flat specific star formation profile. So there is an indication that bulge and disk component build hand in hand. When we go to more massive galaxies, we see a suppression of the star formation activity in the core, and this is not just because of dust, but actually we corrected for dust, and we still see this reduced activity. And this is mainly driven by the very high central densities that these galaxies already made. So, these galaxies are at redshift 2, but they have made their central stellar mass density already previously. And so they have very comparable stellar mass densities to the local early type galaxies. And so at the end, what I would say is that at least from this observational perspective is that we don't need to change the morphology of a galaxy dramatically when we switch off their star formation. Okay, So thank you very much for your attention.
Questions?
And I have just like a more general question. So very nice talk, first of all. I mean, one of the nice things about this meeting is like hopefully connecting, like, because in the smaller scales, like we know a lot about how star formation happens,
Yeah.
and, like possible quenching mechanisms and stuff like that. But sometimes it feels like we're speaking different languages.
Yes.
And so just wondering, like, what kind of things, like, yeah, would you want to know about the star formation process in detail that could like help solve some of these questions that you're looking at?
Yeah, I mean, observationally, we are not able to, at least we want to understand how star formation takes place in redshift 2 galaxies, where the interstellar medium is very different. I think it would be nice to get observational quantities from these high resolution simulations that we have seen on like parsec scales on kiloparsec scales. Because at the moment, I mean, at least I enjoyed the conference very much, but for me it was very difficult to understand how we can link these parsec scales to the kiloparsec scale that we are able to resolve now, and also with JWST, we will not. I mean, with lensing, we will see certain galaxies with a high resolution, but it will be hard to overcome the kiloparsec scale. Maybe we can measure 0.5 kiloparsec resolution, but we don't get into a very high resolution regime. So how we link these kind of very high resolve things to the
I wonder if you can use like one as an analogy for another, right? Like the overall properties of this cloud are similar to this whole galaxy, so maybe you can learn. I don't know if that's one approach, but
Yeah.
it's a good question.
Yeah.
John?
Yeah, I'm not sure I understood your one slide where you tried to show how you could explain the dispersion in the specifics in the star formation main sequence as some kind of evolution.
Yeah.
And I think you did it for Z equals 3. Could you put that again?
Well, yes. So the main point is that so you can think of that you have star formation in a galaxy, that is maybe an exponential disk or so, and then you need to. I mean, it's kind of like redshift 0 when you have a merger. You drive in a lot of gas into the central region. And the thing we put forward is not that different from that. You can take more or less the redshift 0 picture, but you don't need to have a major merger to to redistribute the gas. You can also have already a counter-rotating stream that brings in a lot of gas into the central region. This is just because these galaxies have much more gas, and so you don't need a big disturber to do that. But the main idea is that you redistribute the gas profile that you have into a more compact gas profile.
Right, but what I guess I didn't get is that I thought that the dispersion was independent of redshift, basically. So I would think that a high redshift, that you might find a wider dispersion rather than the same dispersion. So if that's going on at high redshift, what do you think is going on at Z equals 0 to give you the same dispersion?
The same dispersion, yeah. That's an interesting point. I mean, the thing is that, I mean, why do galaxies can go above forever? They kind of self-regulate themselves, and I think that's the thing that feedback kicks in, and that's probably the same mechanisms as at low redshift. So that that the galaxies is able to form a lot of stars, but then these actually first of all the gas gets consumed into stars, but the stars themselves also drive outflows, and so you are reducing your star formation activity again in a self-regulated manner. But concerning the scatter, I mean, first of all, the simulations must always not be trusted 100%. I mean, the problem is, of course, that those simulations are not able, I mean, like most of the simulations are not able to trace through the very high density gas phase, so we are not able to reproduce starburst systems that are significantly above the main sequence. And so the scatter itself in the simulations, would be not trusting 100%. As well as in observations, I think we don't have a good handle at the moment on, below 10 to the 10 solar masses on what really the dispersion is at early times in these galaxies.
I still struggle to understand to what extent you actually care about star formation. Because your first bullet point here seems to say that you actually don't really care too much about the physics. It's all going to be the same star formation efficiency anyway.
Yeah.
And then the only thing which I can take away from this slide,
Mm-hmm.
where you actually seem to be caring about the star formation physics, would be the quenching.
Yeah. Yeah. So I think the information is encapsulated in the redshift, independent efficiency. So that this is a simple abundance matching model, and you kind of have a, how efficient are you producing stars in a certain halo mass? And the question, I mean, I think all the physics is lying in that. You see, the model is not telling you what the physics is there, and this is, I think, is exactly the important question. So at least for galaxy view angle, I think for the lower mass halos we have a somewhat good understanding of how this works. And at higher masses, the quenching is exactly the open problem. But I think it comes in with the efficiency. So it's when you have if you take this efficiency as given, you can just put in the evolution of the halo mass function, and you can reproduce the cosmic star formation rate density. So it is the question on the scale. I mean, if you are interested into the efficiency and how this varies the halo mass, I think the star formation physics is important. Yeah.
So that's thanks, Andre. Okay, and this is the final talk of the conference. The research talk by Ben Martin.
We get a little bit more light.
Yeah, that would be helpful. Actually.
So we got light, now we need a projector.
I do not know.
What's going on with the projector? It's not liking me.
Well, projector and level of lights.
Let's see.
Do you have HDMI?
I do.
Try this one. Unplug it.
Projector maybe. There we go.
And then how do you want the lights?
I don't really care. I don't have many super fancy graphics or anything.
Put them to almost all the way off, or like this. That's the choice.
Leave it on because I'd rather people be awake,
By the way, can I just, while we have this little short break, I found some spare change, and I might be able to take a lot of people to a Chinese restaurant after this. So if you're interested in some Chinese food after this, could you raise your hand? Let's see how many people. Only very few.
Clarify that you're buying.
What I'm buying. So, 7, 8, 9, 10-ish. Okay, thanks. I'll be right back.
Take your time. All right, last talk of the conference. I know you're all tired, so I'm going to jolt you awake by telling you how badly we do star formation in these cosmological simulations. If you're not shocked after this, I'll be disappointed. The word adventurous in the title should tell you that it's a total mess. That's not star formation, that's what I'm going to talk about right now. This is work I'm doing with a large collaboration here, people who work on illustrious, some who don't. But how many of you by now know what illustrious is? Show of hands. Excellent, awesome. So we can go right to the movie. So illustrious is a cosmological hydro simulation. The whole question we're asking here is, can we predict the galaxy population that we see in the real universe? And the results from these simulations have been very encouraging. In fact, there are a lot of things that actually kind of check out. But at the same time, we have a lot of free parameters. We have a lot of these subgrid models that we put in by hand. Namely, like, this is all the physics that we can't really resolve. But putting in these subgrid models is not just an exercise in matching observations better. It's also kind of what we want to learn from these simulations. And I mean, that's the physics that goes on in galaxy formation. How do we improve that? Well, we find observations that the simulation cannot explain, right? And they will tell us in which directions we have to push our models, our physics. And one of these models is star formation. So how do we convert the gas up here into these stars and illustrious? Just out of interest, how many of you know how this is done in these cosmological simulations? Yeah, this is the last movie or really super visually amazing slide though, so I would say let's turn the lights on.
Okay, well, okay, have you seen it? All right, sweet. All right, let's talk about the star formation in these simulations. I want to emphasize that this is not quite like what Sandro was just talking about. He was showing these zoom-in simulations where you're essentially simulating one galaxy. And there you can do things, like where you just look for cells that have a very high density, I don't know, 100 per cc, and then you say, okay, they're forming stars now, boom, you put a stellar particle in there. But in illustrious, you cannot do that anymore because the cells are so big, we're talking, I don't know, half a kiloparsec, that you just never get to those densities. Because what's really going on is that inside of your cell, you have both a hot interstellar medium, you have many, many GMCs, many star-forming regions. And so we have to make a model for how the star formation proceeds. This is the famous Springel and Hörnquist 2003 model. And the model is exactly that. It takes into account, sorry, my pointer isn't working very well for some reason. Oops, sorry. It takes into account star formation. That's when you take cold gas and make stars. It takes into account supernovae. It takes into account cloud evaporation. So in the supernovae, heat cold gas to be hot gas. And it does the opposite when hot gas cools to become cold gas. Don't worry about any of these equations. The point is that, amazingly, you can solve the system in equilibrium exactly. And so you get, just from an input density, you get a star formation rate, you get a supernova rate, you get an effective equation of state, you get a temperature, you get it all. It's kind of like magic. And it actually does pretty well. So here's the stellar mass function observed in gray, and then in the old illustrious, that's red, and the new illustrious, the TNG, in blue. And it matches very nicely. But I'm not here to tell you about how great the illustrious is. I want to highlight that these two are actually quite different. Right? So between the simulations, the low mass end got a lot better, and the star formation recipe did not change. It's the same. So this difference is because the feedback was changed. The feedback at the low mass end was made more efficient, so more gas gets blown out. And that highlights that just because you match properties like this doesn't mean that you're doing everything right. Right? This does not necessarily tell us that our star formation model is correct. It could also be that the feedback sort of makes up for it. And so effectively, we can never be sure that we aren't getting the right results for the wrong reason. How do we convince ourselves of whether that's true or whether we have to improve something? Well, I would say let's use some other observations. How about gas? How about H1, H2? If we're making the right amount of stars but have totally wrong amounts of molecular gas or atomic gas, then that to me would be an indication that we're not really doing anything. So let's see. So why not make a plot like this? Just classical H1 mass as a function of stellar mass. Put some observations here. And now put illustrious on this plot, right? The problem is that we don't have this quantity in illustrious. Because in these simulations, we aren't following explicitly the creation and destruction of atomic or molecular hydrogen. All we have is one gas density. And so that's going to be the starting point for this talk, is how do we even start comparing to observations when we don't even have that? So what we have to do is we have to post-process. We take the simulation, and then we have to make a guess for how much atomic and molecular hydrogen there would be. Other people have done this. This is from the Eagle simulations, basically the competition. And I mean, it's up to you if you think that's reasonable or not. But why are there two lines? That's because there are different ways to post-process. Let's look into that in some detail. For concreteness, let's look at one example galaxy. So here I've picked a 10 to the 11 stellar mass galaxy. This is the stars, gas, temperature, metallicity, star formation rate, and the neutral fraction. And how that's computed is a whole different talk. So this thing is star forming, has like a star formation rate of 0.2, so we'd expect there to be some molecular hydrogen. How do we now guess what that would be or where it would be? Well, one way would be just rely on observational correlations. Right? It's long been known that you have this beautiful correlation between the molecular fraction, so that's H2 over H1, and the pressure, where pressure here is measured in this funny way, this mid-plane pressure that is derived from certain surface densities and velocity dispersions. Now, what people have been doing classically in these simulations is say, this is, it's too complicated. Let's just use the pressure in any given cell, and then for each cell you can guess what the molecular fraction is. Very nice, that's super easy. Let's do that. What we get is not a lot of H2, right? So black is 0 and white will be 1, and I see black. And it's not your eye, it's not the projector, there really isn't any. So this is, again, the neutral fraction, just to remind you. So this is molecular as a fraction of the neutral gas. Anyway, point being, there isn't any in this model. What we can also do is we can go to simulations where people have been following the real chemical network. When we do that, we get something like this. This is from Nedden and Kraftsov's model. And there we get some H2. Good. And then we can also use analytical models. So, they always go something like you have a cloud, it's spherical, or a slab, and then you have some UV radiation from stars in the UV background, and they will dissociate H2. So you have to build up some H1 shielding column, and then once you get past that, then you can have some H2. So here is what happens when I use the Krumholtz 13 model. That actually predicts even more H2 for this particular galaxy. Now you might say, okay, that's only one galaxy, who cares? But it turns out that these trends actually are maintained, right? I mean, if you look back, these all look totally different. This is a pretty bad sign to me. And this is borne out. So this is a full sample from illustrious TNG. Each line is one of these models, and you see they vary from what, 0.1, 0.2 to 0.7, 0.8 molecular fraction. Yeah. So great agreement here. I should say there are many, many complications, right? Like how you compute the UV background and so on. But I think the point stands, right, that you can't just use one of these models and say, oh, I know what I'm doing. Clearly, we don't understand what we're doing here. Now, moreover, the way we computed some of this stuff was pretty silly, right? So I told you here we're just taking the pressure in each cell instead of really doing what the observers did. Here, actually, a lot of these models rely on surface densities, and people just use volume densities and sort of convert them in some more or less ad hoc way. And so I thought I'd go a bit further and try to do better. So here I've computed the actual midplane pressure according to what people have measured in observations. So you really use the surface quantities, measure velocity dispersions, and so on. And lo and behold, we actually get some H2. And here I've taken real surface densities and so on, just try to be a bit more careful about this. And in fact, it looks a little better. So the dashed lines now are each of these models, but computed in a more sensible way than people have been doing in the past. And it's not great, but they're at least, in the same, I would say, half of the plot, so. gotta take it where you can find it, right? So let's go back to our H1 plot now. So now we can put illustrious on here. Again, these solid lines are the sort of naively computed models, and dashed are the slightly more smartly computed models. And because H2 is a small fraction, and they're like 5 orders of magnitude, so now they look at least closer together, the lines, that's good. But still, you can still get some pretty big differences in your prediction. So we still have to do some work on this, but I think as we go along, as we improve these models, we can hopefully come to some sort of reasonable agreement here. And my goal for now really is to, A, compare to observations, of course, but also really give everyone who uses the simulations a big catalog of these different predictions and let people play around with it. This will be public as soon as the simulations are public, of course. But most importantly, I want to warn you again, this is all super preliminary. Please do not call me on any of these plots. There could still be bugs and things that we simply haven't understood about how to use these models properly. All I want you to take away is that, it's really crude, right, compared to all the things we've been hearing about in these last 3 days. I think I even saw plots in like CGS units. It's amazing. We don't have those scales here. It's all kiloparsecs and averaging and silly approximations. And it leads to situations like this where you can't even really predict the observables very easily. You have to really think about it. But hopefully making some comprehensive catalogs and model comparisons will help. And I'm really looking for guidance from all of you, right, as to what observations would be most discerning in what our models are doing and what you think is most important to improve in these simplistic star formation models. Thanks.
Oh, I mean, I think you have them in Illustrious. I mean, it actually matches morphologies pretty well, like in terms of both elliptical, spirals, and totally irregular stuff. I mean, if you look at the movie, you could see, I mean, there's some pretty weird stuff even in there. So I'm not sure I can give you a totally specialist answer. I haven't looked at this myself. But I think that's actually one of the things that is looking pretty reasonable.
I might have missed something that you said, but would dust be any better than atomic and molecular gas? Could you do that any better?
I haven't thought about it. I think it's, I mean, you obviously also have to come up with some post-processing model.
But I can tell you that I think most people would agree that's less fraught than the atomic.
So if I just give you density, right, that's all I give you, and temperature, metallicity, and so on, can you write down a simple formula for dust?
It might not be right, but yes.
Yeah, well, I mean, right, you know, it's not the standard here, right? So,
It would be more right than trying to get the H1 and the H2 correct, right?
and then from the dust, I mean, would that just be to predict observations, or you mean, yeah, okay, yeah, we should talk about that. That's a great idea.
When you deal with feedback in these situations, is the significant launching of feedback that really drives mass away from the galaxy, is that happening on cloud scale, so to say, which you cannot simulate, kind of approximate, or is this on scales of kiloparsecs before the material actually enters the galaxy?
It's more on kiloparsec scales. I mean, just from the cell size that I described, right, you can only implement feedback on sort of a few cells, right? If you have something like a supernova, you'll put it maybe into the cells around you. And it's a complicated story, right? So it depends. So as I said, in the star formation model in Illustrious, there's already some feedback included in the model, which is supernova feedback. That's built in every time you form a star, basically. But then there's also other feedback, like winds that are being launched, AGN feedback, and so on. And these things, this is like all the knobs I was talking about that you have to sort of carefully tune, right? Yeah, this is where it lies, right? I mean, put in AGN feedback, it sounds trivial. Maybe you just put some energy into one cell. But it turns out that will do something very, very different than injecting momentum in the cells around you or jets or something like that. So in each of these models, when people describe them in a talk, right, there are years and years of really careful, very technical investigations and so on. But yeah, to answer your question, it's more on a kiloparsec scale.
All right, well, let's thank Benedict again.
Okay, so we're almost done. We have like 5 minutes about each conference, and then I have 5 minutes where I have to thank a lot of people, so don't go away for that. That'll be very exciting. So if you ran an unconference, please come join us. Tell us what happened. And yes, everyone's very tired, but everyone desperately wants to know what happened. So just be succinct. Okay. Oh, and the Chinese food does come with beer, in case that changes it.
Is that a house of flowers?
Next to your house.
Oh yeah, that's why I'm happy about it.
Kara, go first, you're at the end.
Sure, Betsy and I jointly ran a session on star formation in extreme environments. Secretly, let's just talk about the CNC, was our secret goal for that.
We had a little more general discussion about what constitutes extreme, not all of which necessarily is satisfied by the center of our galaxy. So anything from extreme physical conditions like density, temperature, turbulence, okay, center of our galaxy checks that off, but of course we don't have an AGN, we don't have a starburst, we don't have low metallicity, which is really interesting if you're looking at early universe things. We have moderately extreme chemistry, but maybe not as extreme as it comes. So there's definitely a range.
Talked about IMFs and how it's weird that they seem to be the same, but it's hard to say if there's really any variations, except for like in the young nuclear cluster and a few other places. Spent a long time looking at our new SMA survey of the CMC. We have like some nice continuum images from that, so we played with those for a little while. Talked about fun data reduction and cataloging and interferometry noise, stuff like that. interesting contributions on like the chemistry stuff in terms of the fact that there's like 8 orders of magnitude lower molecular oxygen abundance than was expected, which I had
Not specifically in the center of our galaxy.
yeah, sorry, just
In general.
in general,
Yeah.
which I had no idea about. But mostly I just looking out about our galactic center, I think.
When will the CMs data be available for the world?
I mean, if you want, I will send you a zip file now. It's not hidden. It's just difficult, and so we want to make sure it's like right before. So paper draft is getting close.
The status is there is a continuum map, and this can be distributed. The lines are still being worked on, and there should be an initial catalog and survey paper out.
We'll see the exact timeline, but absolutely within a year. Yeah. If anybody wants it, just ask. I'm happy to share. At this point, it's probably mostly right.
Just to clarify, oxygen is okay. Like the oxygen abundance is fine. The 67P oxygen abundance. Oh, sorry, molecular oxygen O2 abundance is way, way, way too high. But it says it may have interesting. If it's confirmed, it'll have interesting consequences on where our solar system forms. It would have had to have formed in a very warm cloud, a 20K cloud.
Okay.
If it's confirmed to be actually part of the nucleus.
67.
Oh, sorry. I can't pronounce the whole Rosetta Comet's name.
Oh, okay. Got it.
Yes.
Got it. Thank you for clarifying. I misunderstood.
Oxygen is okay.
Yeah.
The
Yeah.
comet's oxygen is weird.
We took a poll at the end, and we all decided that we think how star formation progresses should depend on the environment, but we don't know how yet. Yeah, still looking for the proof. But we all agree that it should. The fact that the IMS are most of the same is annoying. So. Should matter. That's all.
Yeah. Okay, so we had an unconference on the scatter in the star-forming main sequence, which we just heard all about yet again. So I just thought I'd give one succinct slide summary of what we talked about. So as you all recall from Sandra's talk, there's a correlation between the star formation rate and the stellar mass of star-forming galaxies. It has a slope of roughly 1 and a scatter of about a factor of 2. And so the question is, what can we learn from this, remarkably tight correlation that we observe in the universe? So we sort of listed out a few things that could contribute to this scatter. So a nice, simple theoretical way to think about it is that galaxies of a particular stellar mass have a wide variety of accretion rates, and the range of accretion rates from dark matter-only simulations is roughly that size, 0.34 dex. So there are a few nice models, including my own, where this observed scatter, this spread in the star formation rate at a fixed stellar mass, is just purely from cosmological large-scale accretion. But of course, we've also heard, for instance, from Charlie that the star formation rate correlates very well with the dense gas mass. So another way to think about that is, so this provides another way to think about this scatter in this relationship is that at the higher end you should have more dense gas. And we also heard from Sandra that when you go to the upper envelope of the main sequence, you get compaction of gas into the centers of galaxies. So all these things could contribute, and they're all sort of not mutually exclusive. And sort of an alternative, these other things that don't really fit into that picture are that you could have feedback that really causes burstiness, short-term burstiness of the star formation rate. And there are observational biases and tricks in how you convert the observed photons into the actual star formation rate. And then people brought up a number of complications. First of all, it's not clear exactly how you go from an n-body cosmological simulation to gas that is actually available to form stars. And everyone sort of agreed that maybe all these things are happening, but no, we didn't agree that these all happen at the same time. So if you're observing a fixed epoch of galaxies, it's not so clear that you can draw this nice, neat picture.
So neat.
Okay. So we talked, so I did an unconference session in the afternoon. We talked about stellar feedback. We talked about a range of things, kind of more so like related to observations, and also, talking about different modes of feedback. And basically, if you really understand how feedback affects, like let's say the dynamics of H2 regions for what we observe today, you really have to take into account all the different modes of feedback, because the dynamical structure, or the physical structure of what we observe today of evolved H2 regions is going to be shaped by the combination of the different feedback processes. We also talked a lot about kind of like the challenges in observing these different modes of feedback, and for example, like we talked about Thor a little bit in the sense of like Henrik talked about, like he has these velocity gradients, or this data that kind of shows what's happening in these star forming regions and in this gas, and how can we disentangle that to study how different modes of feedback, or how feedback as a whole is actually generating that, kind of shaping those structures or the velocity gradients that they're seeing. We also talked a lot about feedback on larger scales. So how does feedback, for example, affect turbulence in molecular clouds? And we kind of came to the conclusion in a way, and a lot of stuff that I had learned, which was, when you talk about the large scale molecular clouds, like tens of parsecs, that the turbulence themselves is likely due to global effects, so like shearing and the galactic dips and so on. And a lot of times, people want to understand how feedback itself can actually affect turbulence in molecular clouds. And so we kind of started talking about, well, maybe on the smaller scales, like feedback is important, but overall it's going to be the global properties of the galaxy itself for these large scale molecular clouds. And then also to talk a little bit about the challenges of simulating feedback, or trying to study how feedback affects star formation and simulations, just because to get the true picture, we really need to include all the different components, and that's a challenge.
It's a theme.
Yeah.
Okay, so we ran a session this AM on large-scale galactic filaments in the galaxy, which has been brought up a few times in this conference. So a large-scale filament is anywhere from tens of parsecs to 250 parsecs, which can be traced in CO, but also a lot of them can be traced primarily through their very dense gas. And so the main question we're trying to answer is what fraction of these filaments could be associated with spiral structure. And so not just spiral arms, as Alyssa likes to remind me, but maybe interarm regions or spurs, in which fraction may have no association whatsoever with galactic structure and just sort of controlled by smaller scale forces like local self-gravity rather than sort of this external gravitational spiral potential. And so one of the main questions we have to ask ourselves is, how do we actually distinguish between these different populations? And we talked about how kinematics are going to be crucial. So we heard from John Henshaw back here, who's doing he's made a really great algorithm called Scouse, and also Leotis that looks at the kinematics of these filaments in very great detail, looks at their velocity gradients. There's been some recent work by, I think you're working with Sarah Reagan, to look at two different giant molecular filaments, these large 1 degree filaments of dense gas with these very large CO envelopes, sort of what velocity signatures distinguish between the inner arm and the arm filaments. So how that arm filament should have a larger velocity gradient than the inner arm filaments. And this is also consistent with some recent simulations by Claire Dobbs, who we'll be speaking with tomorrow.
Tomorrow at 11 a.m.
11 a.m. Yes.
Pratt. So it's like some other room downstairs in the building. Find one of us who can take you there. 11 a.m. is the ICC colloquium. She'll be talking about lots of things that were talked about at this conference. So please come if you're still around.
So Claire Dobbs is here. She attended the session and she talked about how she did some recent work with Anazor Cabral, with Exeter. She had to that Exeter as well. They looked at giant molecular filaments and how these large CO filaments are mostly created in the inner arm region via galactic shear, that we'd actually see them as CO features. So mostly they'd be sort of atomic features in the interarm region. So when you reach the sort of the deepest point in the gravitational potential, well, it becomes dominated by CO, and you can actually see the longest CO extents. So that's primarily when we would sort of observe them. We had a contribution from Mark Reed here, who very valuable contribution about how we could possibly get some parallax distances to some of these Nessie-like bones of the galaxy that we've been working on here at Harvard, which is also actually a GMF, and how if we have enough H2O maser activity, we could apply for time. And it would be a moderate proposal, and so we'd actually be able to see whether our hypothesis that this filament is forming in the Supertorus arm in the midplane at a distance to a known spiral arm, whether it's actually consistent with the other points that trace out the arm in Mark Reed's very pretty spiral arm maser view of the galaxy. So that's the summary of that.
Well, let's thank everybody for the conversation. Can everybody from the CFA and Heidelberg organizing committees come to the front? Some of you just stay there.
At the front.
I have little pretzels here. So this was inspired by Anna. Anna just moved here from California. She's really, really worried that she's going to be cold. Everybody, and so she's going to take the blankets from everyone. Where's Hope? And then we were worried that for our colleagues who have to go on an airplane, that's too big to put in a plane, but if you want one, we can give you one. So instead, you have your choice of CFA hats.
Of course it can.
See? For Germany. See? There you go. Yes,
Okay. This here.
Oh, we get to.
No. I will delay this.
So then I think we have to pose. Can you take a picture? Your close by out that. There you go.
That's on.
Sure. That's all good.
See you later.
Yeah, cape.
Got a new job.
So many people there. You guys want to like push them just a little bit? All right, there we go. 3, 2, 1. Playing 2, 1. Cool.
Wait, and then we can all just say thank you very, very, very much. And I'm very grateful to all of these people, and especially Thomas for suggesting this meeting in the first place.
Okay, but I wanted to thank you. You did a really great job in organizing the meeting, especially three over there. Because we didn't do a lot this time, and we just came. I think we covered a lot of territory during these 3 days. What I found amazing is that there is so much common interest in both places. I mean, we heard about the cosmological simulations. I mean, Volker Spengel is still around the corner, although he now will move a couple of miles towards Bavaria, but the parallax from here is still the same place. So I think we had a lot of fun. I found this meeting particularly good, I have to admit, because at the beginning, you have to learn how the other side works, but now the barrier is full, it's done, and so we can be, exactly. That's exactly the feeling I have, So it was really a great meeting, and I learned a lot, and I hope next year it will be in Heidelberg again. Maybe not in November. If we could agree on a little bit earlier date, that would be good. But we will work on a common date. That's a challenge we always have, I can tell you. So thank you again for a great meeting and hosting us.
Thank you. Some of us will proceed to House of Chang. So just stay around here if you want to go.